Hi, I'm Michael Waite. I'm an associate research scientist in the Department of Mechanical Engineering at Columbia. I work in the Quadracci Sustainable Engineering Lab under Professor Vijay Modi, and the work I'm talking about here was also done with Ryan Iyer and Yuezi Wu. Commercial and residential buildings account for nearly 60% of New York City's total greenhouse gas emissions. Buildings are thus a central element of reducing emissions. So this is necessary to mitigate the worst effects of climate change, but also to meet new laws in New York State and New York City that have building emissions in their crosshairs. Early efforts have focused on efficiency through improved new construction and retrofits of existing buildings. But we've yet to successfully implement measures that can achieve, say, 50 to 80% reductions in emissions, and certainly not at scale. So we can safely assume that to achieve dramatic greenhouse gas emissions reductions, we'll need to consider both the buildings themselves and the larger integrated energy systems that supply them. Through data from New York City, we've begun to get a handle on some of these issues. The unique data set that we have includes monthly data for electricity and natural gas usage for all buildings over 25,000 square feet. But here we focus our initial analysis on the dominant class of buildings, multifamily residential buildings. We focus specifically on space heating, the largest single source of residential building emissions in the US, New York State, and New York City. We also delve into the impact of heating electrification, which means converting current fossil fuel-based heating systems to electric heat pumps. As shown in figure 1 on the poster, we first use this data to get a handle on seasonal energy usage. Through a database model previously published in the journal Joule, we model the temperature sensitivity of building loads and predict the energy usage profile for each building with heat pumps replacing fossil fuel heating. We can use these same models and our understanding of the current electricity grid to compute estimated emissions for these dominant end uses, both before and after heating electrification. We can further see in figure 2 the large variability in electricity and gas usage among this large subset of buildings. By isolating groups of buildings within this full set, we can see in the table that the emissions impact of electrification is highly dependent on current electricity and gas usage. However, in all cases, it is significant, even in the current grid. That's important. Even with the current electricity resource mix, we see a significant impact across the board. We can also see from figure 3, though, that the electricity usage profiles of building changes dramatically with heating electrification. This is because peak heating demands can be significantly higher than the current cooling-driven peak loads. This has implications for distribution systems that serve these buildings and also the larger energy systems, particularly because this is all going to be happening at the same time that we're seeing a larger energy system transition to more low carbon, renewable electricity supply resources. We've developed a detailed linear program optimization model of New York State, the electricity system specifically, and includes a lot of topographical information and very detailed current data on the system. It warrants in-depth discussion in itself, but here we're going to focus on some key takeaways that are relevant to the discussion at hand. First, in figure 4, we challenge the conventional wisdom that renewable energy growth should be prioritized, showing that a pathway that prioritizes electrification can be a more cost-effective means of achieving emissions reductions. Now, it's important for me to note here that this still includes a very large build out of renewable energy. So we're simply encouraging a bit of a shift in emphasis, not a wholesale rethinking or reprioritization of an entire approach. So we can see from figure 5 that in a 2040 scenario, more than half of New York City's electricity supply would come from wind and solar power, and this has significant implications across the board. And we also need to consider the new loads that would accompany this electrification. We show that maintaining current fossil fuel heating for limited use during the coldest weather and heating primarily with electric heat pumps can avoid this very large build out of gas turbines that might be necessary, perhaps avoid a build out of very large seasonal or battery storage, while still more cost effectively meeting the emissions goals. So just to summarize kind of the overall results and what they mean for implications in New York City building emissions going forward and how we can start to look at additional data-driven research. For one, we see that cost-effective total emissions reduction will require heating electrification and perhaps prioritizing electrification. We see that dual source systems that use both the current fossil fuel heating and new electric heat pumps could be a flexible option with both system-wide and building level benefits. Deep emissions reductions lead to a majority variable renewable New York City electricity supply, and this has implications. But we can take all of these things together and note that some level of grid interactive flexible systems in the heating system, something that's not available today, could allow us to utilize both this expansion of renewables and to have benefits at the building level. So in our ongoing research, we'll continue to integrate the models presented here as well as some other novel data-driven analytical methods we've developed. We'll use these to further evaluate how individual buildings, New York City as a whole, and New York State can achieve deep emissions reductions on a pathway to meeting its climate laws and the goals of society as a whole.